Hi, Mick McQuaid here for the third and last time today, day 12, the very last day of week 3, and the very last of our 3 labs for today. So the 2 items in the last lab here are principal components regression and partial least squares. So let's get started. And again, I'm doing the same thing that I did in the previous 2, which is that I've already typed in all the commands, and I'm just going to use those. So one thing though that I should say at the beginning is that this lab, the way that the textbook has set up this lab, it is assumed that you have not turned off R since you did the first 2 labs. So I hope that you have not turned off R. If you have, you'll have to do some reloading. Now you will have to download a new library, this PLS library that's on line 2 of my text here. This is not this is not a library that is part of the base distribution, so you'll have to download it. Okay, so and as I say, I've left R on. I just did the system clear. That simply clears the screen, clears the terminal here. But I'm still in the same R session that I've been in, so I'll be using the same things. If you haven't, you're going to have to go back to those previous labs and reload some things. So, and I'll mention those as we get to them. Okay, so the first thing to do is to load the PLS library. Now, when I downloaded this, I got a warning that one of its dependencies was not available, but I was able to do all of this lab without that dependency interfering. So don't worry about that. That's the RMPI package is not available. I don't even know what it really does, and I unfortunately don't have time today to investigate it. But suffice it to say that it's not necessary for what we're doing. Okay, so we're going to set the seed to 2 so that we can replicate what's going on in the textbook. And the first thing we're going to do is the principal components regression, which is part of this library and which has the same syntax as linear model as the LM function. There are a couple of differences. There's this scale equals true. I think this may be a default, but the textbook uses it throughout, so I'm going to use it. This simply scales the variables. But I think that that's the default. I think that scale equals false is actually not the default. And then we get the cross-validation errors by saying validation equals CV. And we can look at the model with PCR fit. Now, keep in mind that principal components regression is done after a principal components analysis. So we have these components that are linear combinations of the features, and we have as many. We do up to 19 components, but we're really trying to reduce dimensions here, and so 19. You know, it's pretty useless to do principal components regression if you're going to have 19 components, because there is something that you lose with principal components regression, which is that it's harder to interpret because it is a linear combination. So anyway, we get this huge reduction in the MSE, or this is our MSE. So one thing I should mention is that's different between this and the methods that we've been looking at is they report the mean squared error, and this method reports the root mean squared error, which is equivalent to standard deviation. It's the difference between standard deviation and variance. So you have to take the square of this to have numbers that are comparable with ridge regression and the lasso. Okay, so it's just a difference in how they report the numbers. It doesn't, mean any. It's no difference in the math. And in fact, if you square these, you'll get numbers that are comparable to the numbers for ridge regression and the lasso. Okay, and so we can do this. One of the methods on here is a validation plot. So let's do that. So this validation plot shows the cross-validation, the mean squared error for the cross-validation errors. And it should be, if we enlarge this, I think it would be more obvious that the best number of components is 16, which is really a drag because 16 is almost 19. We lose some interpretability in the use of principal components anyway. If principal components is primarily useful if only a few of the predictors are really important. But remember, this is the hitters data. I mean, almost all of these predictors are related. They're all, they're all functions of being a good baseball hitter, and they're all very closely related to each other. So it's not particularly surprising that that this is the result that we get. Okay, so now we're going to do, so this, by now it should be familiar that what we want to do is develop the model using the training subset, then evaluate it with the test subset, and then use in this case, we'll use the number of principal components that we get from that to do a regression on the full set, and that's what we will report as our resulting coefficients. However, to report on the quality of the model, we'll say what we got for a test MSE after doing this training subset and test subset. So let's do this so that we're equivalent to the book. So here's one example of where the textbook is assuming that you've still got the training and test subsets left over from our previous sessions. So if you don't have those, you have to go back to the previous code and rerun it and recreate those. Okay, and then we can do a validation plot of that. And if we do it just on the training subset, we, based on the model that we did on the training subset, this is not, the model on the training subset comes up with approximately 7 as the optimal number of components. So what we're going to do is make a prediction based on number of components being 7. And this will give us the test MSE. And this should be familiar by now. This is the same way that we got the test MSE in our previous cases. And this number, 96,556, if you remember from the previous labs, this is competitive with the ridge regression and lasso results. But unfortunately, it is hard to interpret the results because this is based on 7 linear combinations of the predictors. So now, so this is what we report as the quality of our results. Now we do the PCR on the full data set. And we use the number of components that we found doing this training and test thing. Okay, and so that's it. That's the model that we report. These are the loadings that this is the variance explained by the loadings that we get. Okay, so and the variance. So, and this is actually, this looks pretty good. I mean, even if you eyeball the previous plot, this is probably about where you go to. It sort of it seems pretty obvious if you look up here that it levels off after this point. Look, there are several in the high 46s and 47s, quite a few. So this makes sense as a result. Okay, now we'll move on to partial least squares, and we'll set the seed again so we get reproducible results. We'll do a partial least squares fit, and here we use exactly the same syntax. This PLSR function is a function in the PLS library, the same library that we just used. And we find here that we get the lowest. How did we find that we get the lowest CV error when m equals 2? Okay, so just by eyeballing it. So our lowest number, so we can just eyeball this and we get 391 for CV, and this is an adjusted CV, and so it's comparable to this. So anyway, 391 is the smallest cross-validation error that we get. So we're going to do 2 components. So now what we're going to do is find out the corresponding test MSE for doing it with 2 components, 2 partial least squares components. So this is, again, from the prediction. We get the test MSE, and it's 101,000. It's roughly the same as ridge regression, the last. As a matter of fact, I think it's exactly the same as for one of those. I forget which one now, but it's I think it's exactly the same, maybe as the one for ridge regression. So it's the same ballpark. So now we will do the full model, and then that's going to be it. So this is the full model, but with 2 components. And this 2-component model, so here's a note that that I just jotted down from the textbook. This 2-component model explains 46.4% of the variability in salary. And it's the same percent as the 7-component principal components regression model. And the textbook points out that this is because principal components is only looking for variability among predictors, which we talked about yesterday, while PLS looks at both predictors and the response. So if you can think back to that picture of the ellipsoid and the line of greatest variability, that is the line that principal components is looking for, and how it differs a little bit from the least squares line. That's the point that the textbook is making there. Okay, so that's it for this lab, and that's it for this day, and that's it for this week. So I hope you have a great weekend, and I thank you for your attention, and I look forward to talking to you again next week.